demonstrate how the capacitance of a parallel capacitor varies when you change the different factors on which it is dependent. So this is the parallel capacitor and its capacitance is dependent upon the area of the parallel plates, the distance between the two parallel plates, and also the medium between the two plates. So first of all, we are going to check what happens to the capacitance of a parallel capacitor when we change the area keeping all other factors constant. So for that we have considered two capacitors, capacitor A and capacitor B. And now let us look at capacitor A. For this capacitor A has an area of the parallel plate of this capacitor is 20 into 20 centimeter, that is 400 centimeter square, and we have kept a distance of separation as 3 centimeter between the plates, and the medium between these two plates is air. And we have calculated the capacitance of this capacitor using the formula capacitance equal to area into epsilon 0, that is permittivity of free space, divided by the distance of separation, and we've got a value of 11.08 into 10 raised to minus 12 farad. Now we are actually going to find out the capacitance of this capacitor experimentally. For that we are connecting this capacitor to an LCR digital meter and recording the value. So when we connect our parallel capacitor to the LCR digital meter, we are getting a value of 0.12. It is because we have kept the range in the nanofarad range. Now it is very closer to our near digital value. So when we consider case 1, we have found out the capacitance of capacitor A. Now we are going to capacitor B.
Now we are taking capacitor B, which have two plates with an area of 28 cm to 28 cm, that is 784 cm square. And we are not changing the distance between the plates, that is 3 cm itself, and the medium between the two plates is air. So we are going to calculate it theoretically, the capacitance of these two plates. And we got a value of 23.14 into 10 raised to negative 12 farad. Next we are going to calculate it, measure it using an LCR digital meter. So we are going to connect it LCR digital meter. So we got a measured value of 0.022 nanofarad. And we are converting it into farad, so we got a value of 22 into 10 raised to negative 12 farad. So we can conclude that theoretically and practically it is nearly equal. So we can conclude that when area changes, when the area increases, capacitance also increases. It is clear from the two cases. When we are considering an area of 0.04 meter square, we got a capacitance of 12 into 10 raised to negative 12 farad. And when we consider the phase, when we take the area 0.0784 meter square, we got a value of 22 into 10 raised to negative 12 farad. So we can conclude that theoretically and practically, when area increases, capacitance also.
Now we are moving on to case 2, where we are considering how the capacitance is dependent upon the distance between the two plates. So first of all, we are setting the two plates at a distance of 6 cm between them, and we have calculated the capacitance, which is nearly 5.9 10 raised to minus 12 farad. Now we are connecting our parallel capacitor to a LCR digital meter and recording the capacitance value. We are recording a value of 0.06 nanofarad, which when converted to farad is about 6 into 10 raised to minus 12 farad. Now, moving on to case 2, we are changing the distance between the plates. We are reducing the distance between the plates. And now we have changed the distance between these two plates. We have reduced it to half of the initial value, that is 3 cm. And then we have calculated the capacitance, and we have got a value of 11.8 into 10 raised to minus 12 farad. Now we have connected a capacitor into the digital meter and recording the value of capacitance. We have recorded a value of 0.12 nanofarad, which when converted to farad is nearly 12 into 10 raised to minus 12 farad. So from this observations, we can conclude that as we decrease our distance to half of its initial value, our capacitance value becomes doubles. So this shows that distance is inversely proportional to the capacitance of parallel capacitor.
So we have seen the effect of increasing the area of parallel plates and distance between the two plates. These were done with using the medium as a air. Now let's change it. And we have tried glass as a medium whose dielectric constant, that is K, is unknown. Now first let us find the theoretical value of using medium as air. So C0 is equal to A epsilon naught by D. That means by calculation we get around 88.54 picofarad. That is the theoretical value when we are using air as a medium. Now let's find it experimentally. So we are getting a value around 89. Now let's change the medium and use glass as the medium. Now let's use glass as a medium. Glass as a medium between the parallel plates, and we are getting a value around 0.262 nanofarad. We are getting C1. Now we can find the dielectric constant by the formula of C medium by C0. So C medium is 0.262.
Write in picofarad, that is 262 picofarad. It is equal to 262. Okay.
So 262 by, we are getting
88. Okay.
89. So 2.9. 2.9 is the approximate value that we get for the dielectric constant of the glass.
A parallel plate capacitor with air between the plates has a capacitance of 8 picofarad. What will be the capacitance if the distance between the plates is reduced by half and the space between them is filled with substance of a dielectric constant 6?
So, the capacitance of a parallel plate capacitor whose space between the two plates are occupied by air or vacuum is C equal to 8 picofarad. What we need is to find the capacitance when the distance between the two parallel plates are reduced to half, and also when the space between the two parallel plates are occupied by a medium of dielectric constant K equal to 6. So, let us write the formula for capacitance, that is, again can I help me with the formula? C equal to
epsilon 0.
Thank you. Here, A is the area of the parallel plate, D is the distance between the two parallel plates, and also epsilon 0 is the permittivity of vacuum. So, let's find out the capacitance when the distance between the two parallel plates are reduced to half, and also when the space between the two are occupied by a medium of dielectric constant 6. So, the new D, let's find the new D, that is, Anila, can you please say the new D? It is because the distance between the two parallel plates are half. So, the D will be equal to, the new distance is equal to D by 2. And also, Anjana, can you please say the permittivity of the medium? Okay, 6. That is dielectric constant. Can you please say the permittivity of the medium? Okay, fine. A by D. Here we can see that epsilon 0 A by D is the initial capacitance. So the capacitance equal to 2K into initial capacitance. By substituting the value K equal to 6 and initial capacitance is given by 8 picofarad. So we get 2 into 6 into 8 by 8. That says 96. Any doubts? No. Please feel free to ask any doubts.
What will happen if we change the material of the parallel plate capacitor?
A good question, please down. The capacitance is independent of the material of the parallel plate capacitor. It is only dependent on the medium between the two parallel plates. It is not dependent on the material of the parallel plate.
Prove this question experimentally. So we are using a parallel plate capacitor. This is setup of parallel plate capacitor. So we are taking two cases. Case 1 in which we separate the parallel plates by a distance of 0.8 millimeter, and case 2 where we reduce the distance into half of the initial value and we introduce a dielectric medium with about dielectric constant 5. And so we are calculating the capacitance of this parallel plate capacitor in the case 1. For that we are using a LCR digital meter. Now when the distance is 0.8 centimeter, the experimental value we calculated and found out is about 44.3 picofarad. Now we are going to case 2. For that we are reducing the distance into half of the initial value, that is about 4 millimeter. And then we introduce a dielectric medium of dielectric constant 5. Now for this case, we have reduced the distance between the plates to half of the initial value, that is 4 millimeter, and we have introduced a dielectric medium of dielectric constant 5. And then our theoretical value obtained for the capacitance is about 443 picometer, that is initially 10 times the initial value. And our experimental value is about, using the LCR digital meter, our experimental value we obtained is about 51 picometer, which is nearly, and the experimental value we have obtained using the LCR digital meter is about 451 picofarad, which is nearly equal to our theoretical value. So in this case, we have observed that after introducing a dielectric medium and reducing the distance to half of the initial value, our the capacitance we obtained is nearly 10 times the initial value. So this is actual experimental proof of our question.
The plates of a parallel plate capacitor have an area of 90 cm square each and are separated by 2.5 mm. The capacitor is charged by connecting it to a 400 volt supply. Question A. How much electrostatic energy is required by the capacitor? We are provided with the area of the parallel plate capacitance, that is 90 cm square, and converting it into the SI unit meter square, it is 90 into 10 raised to minus 4 meter square. We are provided with the distance D 2.5 millimeter, and we are converting it into the terms of meter, it is 2.5 into 10 raised to minus 3 meter, and we are provided with the voltage V is equal to 400 V. We are asked to find the energy stored between the energy stored between the parallel plates. So we are finding U is equal to, can you please tell the formula for U? Half CV squared. Thank you. Now we are not given the value of C, but we have another formula for C in terms of area and distance. Can you please tell? Epsilon 0 A by D. C is equal to epsilon 0 A by D. Now applying that formula into it, we get half epsilon 0 A by D into V square. Now we are given the values. Let us substitute it into the equation. Half. What is the value of epsilon 0?
8.854 into 10 raised to minus.
Thank you. 8.854 into 10 raised to minus 12 into what is the value of area? 9. In the terms of meter it is 9 into the distance into the voltage is 400 square. We are using 400 square here. Divided by the distance D is 2.5 into 10 raised to minus 3. Now calculating, we get the value of U, that is the energy stored, is equal to 2.55 into 10 raised to minus 6. What is the unit of energy? Joule. So we get the value 2.55 into 10 raised to minus 6 joule. Now we are asked to find the energy per unit volume. What is the formula for energy per unit volume? Anyone of you can say? Energy per unit volume. We have energy per unit volume. U dash is equal to total energy U by volume. Volume is area into distance. So the total energy is 2.55 into 10 raised to minus 6 divided by area 90 into 10 raised to minus 4 into distance 2.5 into 10 raised to minus 3. So we have to calculate the values. We get 0.113. What will be the units? Joule per meter cube. Thank you. We get the value joule per meter. Now next question.
View this energy as stored in the electrostatic field between the plates and obtain the energy per unit volume U. Hence, arrive at a relation between U and the magnitude of electric field E between the plates.
We are asked to arrive at a relation between unit energy per unit volume and electric field E. So let's take total energy U is equal to. Can you please tell the formula for energy in terms of charge?
Half Q square by
Half Q square by C. Now what is Q?
Q is sigma U.
Sigma U. So Q square is
Sigma square.
sigma square A square, and value of C is, what is C? So sigma square A square by A epsilon 0 by D. Cancelling both the A's, we get the formula half sigma square A D by epsilon 0. Now we are asked to find relation between electric field, but we don't have a term related to electric field. So what we can use sigma by epsilon 0, not by sigma by epsilon 0. So we have sigma square. So what is the formula for electric field? Sigma by epsilon 0. So we are having sigma square. So we are multiplying epsilon 0 in both numerator and denominator. So we get half into sigma square epsilon 0 AD by sigma epsilon 0 square. So sigma square by epsilon 0 square is electric field square, E square. So we get half E square epsilon 0 AD. We are asked to find the relation of energy per unit volume. Energy per unit volume is energy by AD. U is, can you please say, U is half E square epsilon 0 AD divided by AD. So the AD and AD will get cancelled. We get half E